review the axioms of probability only so briefly because I don't know that these will directly come up on the exam, but I think it's important to know the basic idea of this. So the first axiom, I'm just going to write these in as we go. The first axiom can be characterized this way. For all events where our event space, we could denote with that script S, we believe this, okay? The probability of that event is going to be an element of the real numbers, okay? And that probability is always going to be greater than or equal to 0, okay? This comes from more theoretical measure theory ideas, but that's really all you need to understand from the first axiom, is that those probabilities are going to be bigger or equal to 0 at all times if the event is something real from our event sample space. The second axiom, on the other hand, okay, says if we have that entire sample space, so let me talk about the idea of an entire sample space is the collection of all events, if you recall. So if we have the collection of all events, the probability of being in that sample space must be 1, or else we don't have an exhaustive sample space. So this again gets at some measure theory concepts that I'm not going to get into, but I think we can recognize why that needs to be true. And then our third axiom, okay, is the following. If I take the union of an infinite sequence of events that are special events, okay, so this is a countable sequence where they're mutually exclusive or disjoint. So the EIs are disjoint or mutually exclusive. This means non-overlapping. So they have no outcomes in common. Another way to say it. Well, guess what? If that's true, then that's the same as the probability of each of those individual events summed up. So that probability of the union of all of those events is this infinite sum of the probability of each individual event. Again, this seems so clear, but we must make these assumptions to go on and define our probability rules, okay? So in the next video, I'll do the probability rules. So now we're going to go over 2 fundamental probability rules. The first, I'm going to define kind of our setup, okay? In order to define these rules, we need to think about A and B are just events in our sample space, okay? These may be overlapping or non-overlapping. They may be independent or dependent. We're going to talk about those specific cases as we go through these. So the first one is the addition rule. This, by the way, can be proven, and if you take probability with me, we go through a lot of work to understand this in detail. And the addition rule just says the following, that the probability of the union in A and B is equivalent to the probability of A and the probability of B minus the probability of their intersection. Okay? One way you can visualize this is not at all a technical proof, but let's just draw some events that happen to have a bit of an overlap. The union is everything within the circles, okay? So that entire region encompassed by the circles there. Well, I could show you that if I add in A, I'm adding in all of that area that's contained in A. Then, alternatively, if I also add in B, I've added in that region of B. So we've taken care of the union of A and B, but even a little bit more, because notice that crevice in the middle has been counted twice, and that's why we need to subtract it off. So that kind of intuitively gives you a sense of why this addition rule works. Notice that in the event that events are disjoint, there's no overlap. And so the probability of A and the probability of B is the union because the probability of the overlap, A and B, is actually equal to 0 because A and B is the empty set. Okay? So this rule works whether we have overlapping or non-overlapping. There's another probability rule that we need to understand though, and this is the multiplication rule. And the multiplication rule says the following. For any two events, A and B, the probability of A and B being true is the probability of A given B times the probability of B. Or conversely, I could write it this way. The probability of B given A times the probability of A, depending on what you have and what A and B happen to be. Okay? So this is getting at the idea that the intersection between two events can be thought of as the multiplication of the conditional probability of one event given another times the singular probability of an event. And this works for any two events whether they are independent or dependent. Now I'm going to talk about a special case where we apply the multiplication rule in the case where we have independent events, and that will simplify this rule, but I don't like to emphasize that on the outset. Before that though, let's do one example. Okay, so let's say you have a bowl and it has 10 red, 20 blue, 15 green marbles. You're going to draw two marbles without replacement. That means you draw one, you don't put it back in the bowl. You keep it out. And so the probabilities of getting a red, getting a blue, getting a green are all going to change. So let's find that probability that both marbles are going to be red. Okay, so first we need to define some events. Okay. Let's call R1, the event that the first is red, and R2 is the event that the second is red. Okay, so then the probability that both are going to be red is going to be the probability of R1 being true and R2 being true. Okay, so notice application of the probability rule would give us the probability of R2 given R1 times the probability of R1. And I could have said that it's the probability of R1 given R2 times the probability of R2, but that doesn't actually make sense here. Let's continue this on the next video. Okay, so continuing with that example, I was mentioning that we could have written the probability of R1 given R2 times the probability of R2, but that wouldn't actually make sense because the probability of getting a red on the second draw is dependent upon what happens in that first draw when we sample without replacement here. Okay, so here we want to think about, okay, what's that probability of, let's start with the second draw here. Or no, let's start with the first draw. That would make a lot more sense, wouldn't it? So that probability of the first draw being red would be, well, let's see. There are 10 marbles and there's a total of 45. So we'd have 10 out of 45. But then we've drawn one red at that point. So on our second selection, we'd have 9 red marbles out of a total of 44 to select from. This, by the way, works out to be approximately 0.0455 or so. Okay. Let's apply this to another question. What if I asked you, instead of the probability that they are both red, but I asked you for the probability that either is red? Either you get a red marble on your first or your second. Another way to say that is in those two draws that you get at least one red. So it could be a red on your first, a red on your second, or you could get a red marble on both. Both of those fit the description of at least one red. So notice here that would be the probability of R1 plus the probability of R2 minus the probability that they're both true. Okay? Whoops, that should have been a 1 there and a 2 there. There we go. Okay, so notice here I've applied, rather than the multiplication rule, I applied the addition rule. So we kind of went backwards in the order that I presented the rules. So the probability of the first being read would be 10 over 45 plus the probability of the second being read is 9 over 0.44, and we know from the previous one, if we just flip up, that 0.0455 is the probability of both being read. Okay, and so that's going to be approximately 0.3813. If you plug that into your calculator, you can check that. So we had a little less than 5% chance of both marbles being read, but about a 38% chance that at least one of the marbles in 2 draws will be read. One applied the multiplication rule because we were saying both R1 and R2 needed to be true, and one applied the addition rule because we were saying either or should be true. Okay, so to finish up the probability section here, I want to make sure you understand a couple of important terms. First of all, disjoint or mutually exclusive events. Disjoint and mutually exclusive describe the same thing. If I have 2 events, let's draw them out in a very generic way here. If they are disjoint or mutually exclusive, then they are non-overlapping. So notice these events A and B, very generic events, have no common outcomes. No common outcomes. Okay, now this does not mean that they are unrelated. So for example, being a male or female may be one event, okay, and whether or not you like to go to the movies is another event. There may be an association or a relationship between gender and whether or not you enjoy going to the movies, or there may not be, but that doesn't mean that they are overlapping, because these completely encompass different types of events. Okay, maybe a more applicable example, rolling a die. If event A is even number and event B is odd number, then obviously there's no overlap. There's no common outcomes, because A would be 2, 4, 6, B would be 1, 3, 5. Okay, so those are examples of disjoint events versus independence. Often in class I will say, students, okay, we've talked about this idea of independence. Independence again just means that the occurrence of one event does not affect whether or not another event occurs. And I'll ask students to draw what they think independent events in a Venn diagram framework look like. And what they will often draw, you know, last time I taught this, I think I had nearly 50 students in my class, and everybody but one student drew something like this. Okay, so we know from our last slide, these are actually disjoint events. And in fact, almost all the time, these are, I know by looking at these that these events A and B will not be independent, but will actually be dependent. There's only one specific case where non-overlapping or disjoint events could be independent, and I'll talk about that in a moment. So in fact, this is wrong, okay? And if I were to draw independent events, I just in the most generic way possible, I draw something like this, okay? And the reason for that is independent events say that the probability of one does not affect the probability of the other. So I could make a statement like this. Using our multiplication rule, the probability of A and B is the probability of A given B times the probability of B. Well, if these events are independent, then the probability of A given B is just the probability of A. And so this breaks down to the probability of A and B is just the multiplication of those individual events. Okay, so actually it's very difficult for independent events to also be disjoint, because notice this would be making the claim when events are disjoint, that implies that the probability of A and B is actually 0, because A intersect B is the empty set in this case, which would then imply that this must be 0, which would then imply that either this is 0 or that is 0 or they're both 0. So the probability of at least one of the events needs to be 0 for non-overlapping events to be independent. So that's why I would more generally draw them as overlapping events, so that this kind of makes some sense, because otherwise we don't want the probability or one of the events to just be the empty set or have a probability of 0. So make sure you understand that issue. Independence comes up in more applied settings, but you'll really need to check it using this rule, the probability of the intersection of the events being the probability of their individual probabilities multiplied.